binomial probability. So let's just look at this paragraph up here. After spending time determining probability in the previous 3 sections, we're ready to deal with a very special probability situation called a binomial distribution. The binomial distribution occurs when a trial is performed in times with each trial being independent from the other trials. There are only 2 possible outcomes of each trial: success or failure. So the way I look at it is either it will happen or it won't happen. The probability of success is P for all trials, while the probability of failure is necessarily 1 minus P. So it's the other side of the coin, if you will. It's the complement. Remember that word. Okay. So, and keep in mind success and failure. Success doesn't mean that it's a good thing that happens and failure is a bad thing that happens. A success could be something bad. We have a scenario in a minute we're going to look at with students, percentage of students that default on student loan, which the study, that is considered the success. And then if they don't default, then that's considered a failure. But it's the way the problem is proposed. So let's look at the 4 requirements. The same experiment is repeated a fixed number of times. Only 2 possible outcomes, success or failure. The probability for success of each trial is constant. So it's the same probability as you run through that for the success, and the trials are independent. So let's look at the scenario here. Before we get to a general equation, and there is one, okay, so there is a formula. We can figure this out with a demonstration, so I do want to take the time to show you that. So the probability that a randomly selected person, and we're picking at random. Let me just start over. The probability that a randomly selected person is a parent is 3/10. 4 people are chosen at random. So there are tests that you do in a statistics class that shows that they're independent. We're going to look at this chosen at random as independent. We've got the probability that a person selected as a parent is 3/10, or let's see, that would be 30%. So we've got the probability, it's constant. There's only 2 outcomes. You either will be a parent or you won't. And the same experiment is done for a fixed number of times. And we're going to do it for 4 people every time. Okay? So it is a binomial distribution, so we can use our formula. But right now I'm going to show you the pattern. Find the probability. And in fact, we want to start here. This is going to be A, B, C, and then we're going to end with this one. So we want to find the probability that exactly 1 is a parent. So what I want to show you is something I concocted a little bit earlier today. So I listed all the possibilities. Yes, if you're a parent. No, if you're not a parent. And there's 4 people chosen at random. So I literally listed, and you're not going to have to do this, but I think you need to see how it works. I've got 1 way that all 4 can be parents. I've got 4 ways that 3 can be parents. So I listed every outcome. I have 6 ways, 1, 2, 3, 4, 5, 6, that 2 of those can be parents. See the 2 yeses? Okay. And then I've got 4 ways that 1 can be chosen as a parent. And then I have only 1 way that none of these can be parents. So when I first started looking at this, I thought it was a permutation because it looked like order mattered. But really, order doesn't matter, because this is an individual and this is an individual. So if those individuals got switched, order doesn't matter. We still have the exact same outcome. We've got 2 yeses and 2 nos. So that means this is a combination, because this combination is no different than this combination. So we're going to use the combination in choose R to make those happen. Okay, So that's that. I'll bring this back and refer to that as we go. So if I start out with my new number A, I want the probability that exactly 1 is a parent. So it's going to look something like this. Yes, no, no, no. Okay, let's just pick that one. So the probability, I'm going to leave a space here. The probability that this person is a parent is 3%. Okay. Now, if you think about this, we did this a little bit in the last section. We're borrowing this from the idea of probability and statistics. I've got one is a parent, and the second one is not, and this one is not, and this one is not. So remember, when we incorporate the word "and" when we're doing probability, that means multiply. So that's telling me that this second person is not a parent, this one is not, and this one is not. Okay, so where am I getting the 0.7? The 0.7 is coming from right there. So this is my failure. Okay, now we can even clean that up just a little bit more. Well, that's 3 factors of 7/10, so that's going to be to the 3rd power. But that's just only for this setup. But notice we've got one way. So right here, notice this is 1 is a parent. But I've got these other 2, which if I set them, or other 3, excuse me, if I set those up exactly like I set these up, they're going to be the same. The factors are just going to be in different places. Multiplication is commutative, so it'll end up looking like this. So does it make sense to you that we have to multiply this probability by 4 because that thing is happening 4 times? So when we do that calculation, we're going to get 0.4116 as my probability, or we can think of it as 41.16%. Now I want to draw your attention to something. If I refine that even more, I already told you that that set of 4 right here represents a combination. So if you think about this, we have 4 trials, and 1 is a parent. So when I enter that in my calculator or use my formula, I've got 4 combination, 1 is 4. So it literally counts the number of those that are listed. Okay, so our formula can say 4, choose 1, because we're looking for one parent. This is the X, or the R, and then we've got times 0.3 times 0.7 to the 3rd power, which will give us that answer. Now what you're going to find is that we've got a pattern going on here for the next one. We've got exactly 2 parents. All right, 2. This one is, and this one is, this one is, and this one is not, and this one is not. That implies we're going to be multiplying. So I have 2 factors. I have 3/10 for each one of these, and I have 7/10 for each one of the no's, which really is 3/10 to the 2nd power times 7/10 to the 2nd power. But how many of those do we have? Well, we have 1, 2, 3, 4, 5. There's 6 of those. So what I want you to notice is that if I have 4, choose 2, and you work your formula, you're going to get 6. So we need to multiply those by 6. So the formula is going to look like 4, choose 2, 0.3 squared times 0.7 squared. We will get an answer of 0.2646, which then is 26.46%. Either one of those will work. So let's find the probability that we have 3 that are parents. So that's one scenario. So, whoops, that decimal's in the wrong place. I'll cover that up in a minute. So I've got this and this and this and this. So I've got 3 factors of 0.3 and that 1 factor of is not, because she is a parent, and this is a parent, and this is a parent, and this is a parent. She or he, makes no difference. Okay, so that's 3/10 squared, actually cubed, because there's 3 factors, and then this one is to the first power. But if you go count all these, and what you don't want to do is have to list all these. There's 1, 2, 3, 4. Well, if I have 4, choose 3, you're going to get 4, and it literally counts that list. Okay, so we've got a 4 here and a 4 here. So our little combination formula says 4 choose 3, 0.3 times 3, 0.7 times 1. And when we do that math, we're going to get 0.0756. So that's about 7.56% that all 3 from that particular choice are parents. Okay, so now let's do the last one. And I think you see the pattern anyway, which is definitely leading to the formula. What's the probability that they're all parents? All 4. Alrighty, I've got 0.3. Can you see that I'm going to have 4 factors of 3/10? And there are, in this case, none of them that are not parents. Well, how many ways did that happen? That only happened one way. Okay, so the formula then would be 4 choose 1. Okay, so we know that this factor is going to multiply to 1. I messed up. This is 4. This is 4 in the sample, 4 are parents. Okay, so when that works, sorry about that, we've got, okay, and then of course that thing multiplies to 1 as well. Can you enter that whole thing in your calculator? Absolutely. So I'm looking at 0.3 raised to the 4th power, and I'm going to get 0.0081, or about 0.81% that all 4 in that trial would be parents. So what you've got here is an example of a binomial probability, something that has a probability amount labeled. It's fixed. You've got a fixed number of trials. We've got independent trials, and you can use this form. So now let's do one. Let's look at least at the formula. Okay, so I've got n independent trials. So in our previous problem, that was the 4. The success rate of probability in our previous problem, that was 0.3. The probability of getting X successes, so that's how many, like if we had 2 were parents, then this would be the 2. It also, our little formula looks like this. So in this type of scenario, because it is a function, then that's replaced with X. So if you'll notice, back in the previous problems, this was the number in the trial. There were 4. This is the number that we were asked in each specific problem. Notice the success probability is raised to the power. It matches here. And then your complement, that's 1 minus your probability. That number is always the difference in these. Okay, does it always work that way? It sure does. So let's do this next one. A report indicated that 0.38% of employees found their job satisfying. Suppose a random sample of 6 people were taken. Okay, we're independent. We've got a probability. We've got a fixed number of people that are going to take the test, and we only have 2 outcomes. They either are satisfied or they're not. So this is very typical of a binomial probability. Now, I'm not going to go list all these possibilities. I'm going to use the idea of my combination to make this happen. So I know that my N is 6. I know that my X, or my R, is 4. Okay, and we know our percent is 0.38. And then so I know that 1 minus, so this is the failure, is going to be 1 minus 0.38. So you can enter it that way in parentheses, or you can enter it as 0.62. That's going to be your call. So the probability of exactly 4 are satisfied with their job. Okay, so the 4 goes here. Actually, no, it doesn't. This is the 6. So we're looking at 6 people are in the sample. We've got 4. We're checking out those. So I've got 0.38 raised to the 4th power. These match. And then I have 0.62 raised to the 6 minus 4. 6 minus 4 is 2. So I want you to look at this. 4 plus 2 is 6. These two have to match. These two powers have to add to the n. Okay, just kind of helps things go a little bit faster. You could also, depending on the probability and the number and the keystrokes you want to take, you could easily enter that as well. Either one is correct. When you do that, yes, you can enter it all in one fell swoop. So let's just see if we can get this going. I've got 6, choose 4 times 0.38 raised to the 4th power times 0.62 raised to the 2nd power. And that is not what I got on the first one. So I'm either wrong or I have an incorrect entry. So let's try it again with 4, okay, times 0.38 raised to the 4th. And then I'm going to go times, I'm going to do it this way, 1 minus 0.38, close the parentheses, and I'm going to raise that to the 2nd power. Yep, I think I made an error on my notes. So that's a 120228942. Not sure what key entry I made incorrectly, but it can surely happen. If we want to round that to the nearest 4, it would look something like that. So that would be that probability. It's pretty quick if you don't have to list all those outcomes, because that can get pretty awful. So let's do the next one. Let's find the probability that all workers are satisfied. So that is akin to exactly, if they're all satisfied, that means all 6. So we want the probability that all are satisfied, which I'm going to go ahead and equate that to exactly 6, because that's how many are in our trial. Okay, so we know we have a combination. I'm thankful we don't have to write all those choices down. So we have 6 people. All of those people would be 6 times 0.38. And that 6 matches this 6 times 1 minus 0.38. I get in a real habit of doing that. And so this is 6 minus 6, the n minus r, or the n minus x, which that is to the 0 power. So when I calculate that, I just use my other calculator just to give everybody equal access here. 6, combination of 6 times 0.38 raised to the 6th power. Now this thing, if you're clever, that's going to be 1, because anything to the 0 power is going to equal 1. So if you want to see that and not even enter that 1 factor because it's the multiplicative identity, you don't have to. But if you want to follow your pattern, because maybe you're just being a little intense and you forgot that thing, then you'll still get the same answer. So that's about 0.003, 0 if we're going to round to 4 places. Okay? So that's how many, of the 6 sampled, there's about a 0.3% chance that they're all satisfied. So let's do this last one, and then I'll stop this video, and then we'll move to the next examples. Okay, so let's look at no more than one worker is satisfied. Now that means exactly 0 are satisfied. That means none of them are. None of them are satisfied, or exactly 1 is satisfied. That should make sense. No more than 1 out of the 6, well, that means none of them could be, or just 1 could be. So that word or, remember, in probability goes with the addition symbol. So if we want to think probability of no more than 1, if you want to think about that algebraically, it says less than or equal to 1. You could write it that way as well. So I've got the probability that none are satisfied, or, which is plus, the probability of exactly 1 is satisfied. Okay, so I'm going to have 2 combinations. The first one is that none of them are satisfied, so I have 6 people. I'm choosing that none are satisfied times 0.38 raised to the 0, 1 minus 0.38 raised to the 6th. Remember, 0 plus 6 has to equal 6, plus, now the probability is exactly 1. So I've got 6, choose 1.38 to the first, and then this is going to be, I'm going to do this one differently. I'm going to call that 0.62, and then 1 plus 5 plus 1 is 6, or 6 minus 1 is 5. So when we enter that, the first time I entered this, I don't know what I entered incorrectly, but I got like 1.3 and a whole bunch of decimals. I knew it was off because it was bigger than 1. So that should be your signal that you've messed something up. If you ever get a probability that is negative, you messed up. If you get something that is bigger than 1, you messed up. Everything has to be 0 to 1 in between and including those values. So let me see if I can get this in here. Let me scooch this up. There we go. Probably we can get this all in one line if you're comfortable with that. So I've got 6. Select 2 at 0, but that is 1. So is that. So you don't even have to key those in if you know they're 1. I'm going to go ahead and just follow the motions. Times parentheses 1 minus 0.38. Okay, and this is 6 minus 0 is 6. Raised to the 6th power. Plus, now I'm going to go grab this one. 6 combination of 1, excuse me, choice 2, enter 1, times 0.38 raised to the 1st power, or just 0.38, and then times 0.62 raised to the 5th. So yes, you're allowed to use all those algebra things you already know to simplify your entry in your calculator. Okay, so that's what I get. So that is about 0.2657 if we're going to round to 4 decimal places.